Okay. So this is where we left off?
Yeah.
Okay, yeah. That's all my notes stuff.
Wait, so you took off the review assignment, but you made it extra credit.
Correct.
Okay.
Yeah, so that will be extra credit. Okay, so the last lesson that we learned was volume of solids of revolution. So we did this example. This was the washer method where we have like an outside curve versus the inside. So if we do big R squared minus little r squared, and tie out and remember these are circles, okay, and then we have the bounds, the lower and the upper bound. We integrate that, we'll get the volume of the solid created. So sometimes when we rotate our solid, it's not about the x or the y axis, it's about a different line. So let's look at this one. We have find the volume of the solid generated by revolving the region bounded by the line and the curve about the x-axis. Oh, this is the x-axis. Let me just do this. The worksheet that I just gave you, that one's going to be rotations about lines other than x or y axis. Keep that. We're going to do the notes first, and then we're going to do that. Okay, so let's just graph this real quickly. So y equals 2x. Y equals x. And x equals 1. So basically, that's the region. Okay, so imagine that we want to take this region and rotate it about the x-axis. So what is going to be the outside, or big R? So what's the outside part? Right here, 2x. Now what's the inside part? That's just y equals x. The x equals 1 is not actually part of the, it's the bound in that, where do they intersect? They intersect at 0, so that's going to be my lower bound. And where does it stop? It stops at 1. So x equals 1 is actually just going to be the upper bound of the region that's shaded there. And then what do we have? It's going to be big R squared, so 2x quantity squared, minus, just x squared. It's not always going to be what's above or below. Imagine if you duplicated this picture. Like that. So imagine if this is a solid that's created. Think of your outside part. Your outside, in this case it happens to be the one that's above, but it won't always be the case. Yeah, that's what's on the worksheet. The handout that I just gave you. When it's
not, working a line other than the x-axis,
yeah. So we get 3x squared. It's easier if you simplify this. And then what do we have? X cubed evaluated from 0 to 1. So we just get cut. Yeah, I think that's okay. Mainly on the test, there's going to be a part A and a part B. It'll say, write the setup, and then for part B, it'll say, evaluate. Most of the points are going to be the setup. Okay, let's look at this next page. So now we want to use the region bounded by the square root of x and 1/2 x. So I've already That picture's already drawn. So what do we need to do? We need to first figure out where do they intersect. Well, this is 0, 0. And where else do they intersect? 4, 2. And so imagine this getting rotated about the x-axis. So what's the setup for the volume going to look like? Pi. The integral. What's that? Right. We're going to find the volume of the solid generated by revolving the region about the x-axis. So we're taking this piece and rotating it around the x-axis. And it's going to create a solid, a three-dimensional solid. So we want to figure out what's that volume. Okay, so it's going to go from 0 to 4. And you're right, it's going to be the square root of x squared minus 1/2 x squared dx. You're okay with that? Because we could see the outer part is going to be the square root. So here we get x minus 1/4 x squared dx. Right, just go ahead, if you want, just go ahead and plug it in. We should get, what do we get? I only have the exact answer here. Okay. And I have 8 pi over 3 is the exact answer. But I'm guessing that sounds about right. Okay. That's fine as long as it just goes to 3 decimal places because that's what I'll have you do on the test. Okay. Are we all right with that one? So in the next part, so for part B, let's take that same shaded region, but this time we're going to revolve around the y-axis. Okay. So our shape is actually going to change. It's not going to necessarily be the same volume. Imagine if we take this and we rotate it around the y-axis. So now it's going to kind of look like, if you kind of imagine here, you have a sink. Well, it's going to be like it's going to look like a cone, but like curved inside. If you could kind of imagine. So what's this going to look like now? So remember, this was 0, 0, and this was 4, 2. So, okay, we need to change. Right, change everything to x equals. So remember how it was y equals the square root of x? What would it be in terms of y? So this would be x equals y squared. And what would be the other line? So this would be x equals 2y. Exactly. So instead of from 0 to 4, it's going to go 0 to 2. Exactly. Good, good. So now if we look at which one is the outside, so imagine that you have this kind of cone shape. What's the outer, or the big R? It's 2y. And the y squared is the little r. Does everyone see that? So it's going to be 2y squared minus y squared squared dy. Exactly. So when we change everything to y, we change the dx to the dy. Okay. Show a little bit of work here. So we have 4y squared minus y to the 4th. did you figure that? You did it on your calculator? I don't know what it is in decimal form. You want to check? Is 64 over 15 times 5, does that match? Perfect. Yeah, so we're going to move to the worksheet now. See, that wasn't too bad. And
Number 1.
let's see here. We did. Okay, so let's look at, okay, so we're going to look at volumes of solids of revolution when we're rotating about a line other than the x or the y-axis. Not a z-axis, but like a line y equals, in this example, we're gonna rotate about the line y equals -2.
Wouldn't it be the same as doing change the equation to use like slow the equation down so
So there's a couple different ways. That's a good idea. There are multiple ways to do this, but I'm going to show you in a different area of calculus. How's that? Okay. Okay, so basically the way that you set it up is going to depend on where your shaded region occurs. So the first example I'm going to do is, what if our line of rotation is below the region to be rotated? Kind of like when it's the x-axis. So far, all we've looked at was a shaded region above. But sometimes that's not necessarily the case. So here we have, and I've already graphed it for you, we have the square root of x plus 2 and y equals e to the x. So we should probably figure out where they intersect. Which one looks like the square root of x? The top one. So this is here. And the bottom one is e to the x. And if I draw a line, well, let's take this, y equals -2. So imagine that this region is getting rotated about that line. So it's going to be, there's going to be like an open top and an open bottom, if you will. It's going to like be curved on the outside, and then it's going to have curved inward. If you can just take this and reflect it across the line, y equals -2, that would maybe give you a better idea. So, first thing we need to do, let's find the, before we do our setup, let's figure out where do these intersect. So how do we find those intersections? Okay, so go on your calculator. These are going to be decimals, okay? These are not going to be, yeah.
Okay, so when we do it on our calculator, then we're going to find the intersections at the y.
Right, so I will tell you, we're using this same picture for 4 different examples. So just give me the x and the y coordinate. It'll just make it easier.
0.448 and 1.5.
Okay, so this is 0.448 and 1.564. And this one over here, it is not -20.
Oh, okay, I'll do that one.
Because e to the x does not intersect the x-axis. Remember, that has an asymptote there. -1.981.
No, 138.
138.
Yeah.
Okay, so you know how to find the intersections. You can find it if you didn't have the time right now. But what I would recommend is just figure out the x and the y coordinate, because for each one we're going to use obviously, whenever we're using everything in terms of x, we use the x coordinates. Whenever we're rotating in terms of y, we use the y coordinates. Okay, so if this were just rotated about the x-axis, our big R would be x, the square root of x plus 2, and the little one would be e to the x. But now that we basically added 2 units to our each radius, does that make sense? We've moved it 2 units away. So now our big R, right, our big R is going to be the square root of x plus 2 plus 2. And our little r is going to be e to the x plus 2. So picture, what's the distance from here to here? It's 2 plus the square root of x plus 2. And then look at the inside one. This is going to be 2 plus e to the x. Just imagine that if the line that you're rotating, if you're moving it further away, you're adding to the radius. Okay, if it's getting further away, that means the radius is getting bigger. So this becomes big R, this becomes little r. Right, so we'll look at, we have basically 4 different cases to cover it all. So hopefully, x. Okay, so notice how I wrote it here. I wrote that another way you can think of it is big R can be the outside curve minus the line. This will work every time. So think about if I subtract -2, what happens? You end up adding 2. I wanted to explain it that way because sometimes the line that you're rotating might be y equals 1. Y equals 2. Then it would be -1 or -2. It will work every time. So that's why I wrote this. When the line of rotation is below the region to be rotated, the outside curve minus the line, and then little r is also the inside curve minus the line. Okay, let's set it up. What would it look like for the volume? So we have pi. What are our bounds? Good. Negative 1.981 to 0.448. Okay, the first curve, big R squared, so that's going to be square root of x plus 2 squared minus, good, and then the whole thing is dx. We do, right here. No, just remember, it's just big R squared minus little r squared. And honestly, you can plug that into your calculator, I'm not concerned. I'm more concerned with can you set it up correctly? If you want, so remember on your calculators that program that we did, the volume? The super confusing? If you use it, it's not. So here's where you can change the rotation, change the axis of rotation. So if we enter our curves, so it's f of x because remember everything's still in terms of x. What was curve 1? It was the square root of x plus 2. Now, I don't put in plus 2. You'll see how you just put in the first curve. The second curve was just e to the x. And then our x min and our x max. So just remember, this is just our viewing window. So I would just, like I did mine, -2 to 1 and -6 to 2. So -2 to 1, and then -6 to 2. Remember, not the bounds, that's just the viewing window, so that shows us what I have. So now okay, so our bounds we can enter now. So because this is bounded, right? If they intersect at two different points, we can have the calculator do this graphically. I prefer to just put them in manually, but you can have the calculator find that for you. So I'll just, oh, did I click the wrong thing? Let's see, upper bound, I think I have some issues with my calculator. You should be able to enter both of them. I don't know why I couldn't. There we go. So it'll shade it in. So the nice thing about this calculator program is this will allow you to check your answers on your test, but notice it's not going to show you how to set up the problem. That's why I said the setup is most of the points. But you'll be able to test your setup with the calculator program and see if you get the same answer. Because see, when we press enter, so when we change our axis of rotation, number 4, we can type in -2, and then we'll see, hopefully, if you can kind of picture this, and it'll, well, I don't know, can on your calculator show the axis of rotation there?
Yeah.
And then you could do the rectangles to get a better idea.
It's almost beautiful.
Try to air on it. It's been so warm in here. The rectangles. Okay, so I don't know. Last time when I did the rectangles, my calculator.
The rectangle on this one looks fun.
The rectangles just, the rectangles can give you, see, I don't know, mine's weird. It just gives you a better idea. Like, you can go move your arrow over and do a bunch of these. Just, did you have a question? Put the X's. So when I do the, I don't know why this one isn't working quite the same. So this one will actually show you your volume, 19.725. It'll show you your lower and upper bound. Method is wash here about the line y equals -2. Okay. Does that make sense? How to use that?
And then you check to make sure you're doing it right by putting that math line.
Exactly. So what I would recommend is going back to this and just doing math 9, plug it all in, and your two answers should match up. It should be. If it's not, we're in trouble. Okay, next one. All right, what happens when the line of rotation is above the region to be rotated? It just flips. So instead of the curve minus the line, it's going to be the line minus the curve.
Hey, I got 19.75.
So
you get 2 plus, oh.
So, okay, let's look at the example that we have here. This one is going to be rotated about the line y equals 2. Now, the nice thing is, if I ask you several of these questions, you can go onto your calculator and just change the axis of rotation. You already have the two. Sorry. You didn't need to quit it because we're using the same curve every time.
Well, you told me to check math wrong.
I'm sorry.
It's not taking enough time to get these things.
Okay. Well, this one's going to be a different answer anyway. Because now what's happening? This graph, here's our line y equals 2. We're taking this and rotating it this way. So, can you kind of... So now, what's our big R and what's our little r? Exactly. So this is y equals e to the x, remember? And this is y equals, now which one is the outside? It's the e to the x. So it's r is 2 minus e to the x for big R.
So how do you determine The outside one is after rotation, which is on the outside.
Oh.
Like, is after rotation that then you determine which is outside on the inside, or is it according to the beginning? After.
Okay, so that's why I said, I'm not always, it's not always gonna be the upper curve or the lower curve. You have to kind of use your imagination to a certain extent, and just kind of picture, when you start rotating this, which one's gonna be on the outside? It's gonna be the E to the X. Do we see that?
You just check after rotation.
Right. And then what's little r? That's going to be 2 minus the square root of x plus 2. Okay, so now we want to set up for our volume. Now the bounds haven't changed because everything is still in terms of x. So it's going to be negative 1.981 to 0.448. So we have 2 minus e to the x squared minus 2 minus the square root of x plus 2 squared, and this would be dx. This would not be something I would expect you to do by hand. This would be, show me the setup, and then you can give me the decimal approximation. So now, if I already have this in my calculator here, so I can just go back to number 4 and change it to y equals 2. And notice it's just gonna move everything here.
But because this one's outside, the EX outside doesn't matter. Which is one foot to one to it.
No. The calculator program will know. I guess you could say. It's smart. It knows how to do that. So then you can just click answer and you would have $8.536. Yay. Okay. Better. Just like that. You got it?
Yeah.
Yay, we did it right.
8.536. I'm not taking math on.
Okay, so the next two examples are basically similar to what we saw with the x-axis. Now it's just going to be a vertical axis of rotation.
What? These are f of y.
These are f of y. Now, notice I actually already solved them for x for you, so you don't have to worry about that. But if they were in terms of y, right, remember it was y equals square root of x plus 2? So you would just have to solve so you get y squared minus 2. The curve looks different, and the only reason it looks different is because I changed the viewing window. That's all. And then, right, so let's say I have this shaded region, and I want to rotate it about the line x equals negative 3. So picture it's going like that, going around. So when the line of rotation is to the left, so the red line here is going to be big R, and the inside is the blue. Which one is which? The red one, which one is the red one? This is ln of y, good, and this one is x equals y squared minus 2. Just, again, I took the ones on the previous page and just solved it for x for you. They still have the same bounds, right? Right, so remember it was negative 1.981, comma, 0.138. And this one is 0.448. If you flip it, then you have to change your bounds. Oh.
If you were to rotate it, wouldn't the red one turn to the left?
Say that again. Say that again.
If you were to rotate it, you see that over there, right? what if the red line turns to the left line, be on the left side, and the green line would be on the right side?
But this is the out,
You're looking at it like this, right?
you're flipping it this way, so what becomes your outside curve? The red one.
But I can only move it to the y-axis, it's right to left.
It depends on where you're grafting. It's usually right, well, this would be right to left.
But if you take it when the red line is to the left, if you rotated it to where it's over here.
Over here, yeah.
Isn't that where we're?
But look at the shaded region to the dim one. Where is it in relation to this one?
But I thought.
Right, right.
It didn't determine which one was the
If it
red
was,
line.
then it would be the other, if my shaded region started over here and I rotated it this way, then it would be the other way
And
around.
then you have to the last one that you have to look at it after you rotate. You have to determine which is the.
No, no, I think what, Walker, you were asking like the picture after you start rotating it, what's the outside?
Yeah, we didn't go through that.
No, you didn't.
We didn't say we didn't come in just.
Okay,
the red line.
so when we start rotating it, okay, what's big R? ln y plus 3. So it's going to be the outside curve minus the line. So it's going to be ln of y minus negative 3, or some of you might have seen it's just going to be ln of y plus 3. And what's the inside curve? Good, so y squared minus 2 minus negative 3, so that'll be plus 3. So little r is y squared plus 1. Maybe I can clear it up. Let me finish these examples and then, okay, so what's my volume setup going to be? Now my bounds have to change, right? So it's going to go from 0.138 to 1.564. And it's going to be ln of y plus 3 squared minus y squared plus 1 squared. And the whole thing is dy. I don't know. I actually I didn't even put the solutions in last year. It was, again, it's more, I want you to know the setup than anything.
18.5.
Sounds good.
Can you see this?
Mhm.
Can you get?
You do. Can you clarify? You want to see if you can clear it up?
When you rotate like on the calculator, this becomes watt, so when you do R, say Y minus R watt, it's both like it should be right minus left, this is this one, this one, this is off, this one,
But we should take the outside versus inside instead of right versus left.
We should tell them. I know how you change it, but it's done.
How'd you get?
I don't know how you change the method, but.
I don't know either.
Well, yeah, the method is, yeah. Yeah, but I don't know how you can change the method to tell what you are.
So it's okay. I think the calculator is just going to figure it out.
Why is it doing this?
Oh, you know when I did it the other way. Let me go back here.
You're getting the pie in front. But that won't really make a difference. No,
Yeah, you know what? I figured if we change our bounds in terms of y, we have to change the curve in terms of y. So actually, let me keep the bounds the way they were.
That's what it is.
Oh, you know what? I messed up.
it asks for what line you're rotating around. What does it ask for that again?
Say that again?
Where does it ask you to plug in what line you're rotating around?
Axis of rotation.
I think we got
Yeah, I have to go back.
It's like the setup's right, but it gets like -3. Right.
Oh, it's because you have ln of x plus 3. It should be ln of x plus
Plus
parentheses plus 3. I know. Those parentheses just mess everything up. Okay, so the right answer? Good question. I'm going to change I put my bounds in wrong, so. I have to change my axis of rotation, that's why. It's okay. You could use the x bounds as long as you still have your curves in terms of x. But if you use your y bounds, you have to write it in terms of y. But if I already have this already typed in, then I wouldn't. Like I would just, rather than having to change everything. But here, I need to change the axis of rotation. So number 4. And here's where it's going to ask you horizontal or vertical. So we went in vertical, and it was x equals -3. When to change what? It decides what it, exactly, it's going to decide itself. So there is a method called the shell method. It basically uses cylinders instead. You got 15.540? That's fine. Your calculator is going to just use, any of these can be solved using Washington method.
Now, I thought the difference between my answer and your answer was the read, but I don't know what the difference is.
You guys need to change the.
You didn't change the. I wish my graph wouldn't disappear when it does that. I don't know why it does that.
I just read it.
So, okay, so we look at just the shaded region to start. Ignore this.
But on the last one, it says
After rotation.
I guess I'm not sure what you mean when you say after rotation.
So I was saying to determine big R, little r, you look at it after you rotate it.
So you could see like what's going to be on the outside versus what's on the inside. Is that?
Yeah, like after, because it was a different one and it flipped because after you rotated it, the one on the bottom came to the top, and so that was our big R because it was top, my bottom. But it was after rotation that we determined that.
Oh. Okay, I guess I thought you were asking it in a different way because that's not how I look at it.
How do we determine?
So like on this one here, this is the one we were talking about, right?
Yeah.
I don't know how else to explain it because it's not always top minus bottom or bottom. You can't just assume that. I just picture like once you start rotating it, what's the outer curve?
I guess
Which one is further away from the line you're rotating? Okay.
That's better.
The one that's further away from the axis of rotation is your big R. The one that's further away from your line of rotation is your big R. The one that's closer to the line of rotation is little r. I don't know, maybe just because I'm more visual that I just picture it. But if it's easier for you to just remember it that way. So big R is the curve that's further
Okay.
away from the axis of rotation. Yay, well, I'm glad we figured out a way to sum that up. Okay, so the last one is what happens, and let's see if you guys can put this one together, maybe without me. Try not to look. Let's look at just the example before we look at the rule. So we have the same region, but this time we want to rotate it about the line x equals 2. So can you tell me what's going to be big R and what's little r? Okay, so x equals y squared minus 2 is here, and x equals ln of y is the red one. So which one is big R? It's going to be the blue line. And what do we need to do? Right, it's 2 minus. So it's going to be the line minus the outside curve, the line minus the inside curve, and that's if it's to the right. Like, I don't necessarily memorize these rules. I just look at my picture, I look where I'm rotating it, and then I just kind of think, okay, it's been, like, here.
If it's above,
I know,
right?
it's easier for the, like here, my axis of rotation has been moved further away, right? Here's my y-axis. It's going to be further away, so my radius is getting bigger by 2 units.
So if it's to the right or above, then two minus it.
Exactly. So wait, it's gonna, this one, be careful here. It's gonna be 4 minus y squared. I thought somebody said something different earlier.
Y squared.
Minus a negative.
Yeah.
And then little r is just gonna be 2 minus ln of y. So what's the setup going to look like? 0.138.
You want to simplify the setup? Or is it-
No, you can actually leave it the way, like if you write 2 minus y squared minus 2, and then put that whole thing squared, that's fine. Instead of writing 4 minus y.
Well, but then you want it to be like square 4 minus
Oh,
y.
you mean like FOIL?
Yeah.
No, don't worry about that.
Yeah.
I would never ask you to FOIL the whole thing. So if I change for number 4 my axis of rotation, that's the shape. So you can kind of picture it rotating this way now. Here's x equals 2. And then the answer is 19.78. Okay.
So this one is the big R.
Yeah.
And that, this is the same as this graph.
Is that or exactly?
Okay, so the big R and the one represents the actual equation of the reflection of one. Is this the same, like, is this the graph of 4 minus y squared if you had it in between those two bounds, or no? Is that match like the actual graph that looks like the 92? How that looks like the rest of the Yeah.
No.
But if you like put this in a
Okay.
table function, would that be that?
The distance from here to here, or the distance from here to here, is represented by 4 minus y squared.
Okay.
It's a distance.
Okay.
Remember, R is a measurement. It's a radius. So it's the length of, it's the distance from the axis of rotation to the curve. And of course, the curve, it's not just here and here, it's all around, it's 3-dimensional. So at any point in space, it's going to be 4 minus y squared units away from the line x equals 2. So it's going to be out here at some point, you know. I know, it's really hard because we're working with a two-dimensional board or calculator, and you have to try to visualize this three-dimensionally. It can be difficult. Okay, so that's it for the notes.